The next step in this module is discussing technology-enhanced learning environments. These technology-enhanced learning environments are actually an enrichment of, to a certain extent, classical teaching learning situations, although serious gaming examples are perhaps different, but for the other, let's say, examples, you might say that they do not deviate much from the traditional teaching learning environment. We first talk about inquiry-based learning as a specific, let's say, set of applications, mostly in the domain of science and mathematics. Then we talk about intelligent tutoring systems, then about serious gaming, and then about the MOOCs, so the massive open source online courses, which are often offered, but not always, but often offered by universities, for instance, in the Netherlands, by the TU Delft, and of course the Harvard examples are very famous. Okay, we start with inquiry-based learning. First, a discussion about what is inquiry-based learning, then some examples, I hope they work in this case, and then I would like to introduce you to a debate about inquiry-based learning, which has been going on for several years now, but it's still interesting because of the various points of view in this debate. First, what is inquiry-based learning? Well, you might say that in general, inquiry-based learning has to do with creating knowledge by doing research. So it's the research-oriented way of using technology-enhanced learning environments. We will return to this line of products later on when we talk about computer-supported collaborative learning, but now we just mention a couple of characteristics of these learning environments. So students have to solve problems, have to do research in simulation environments, explore models, vary parameters, and see what the effects are on outcome variables in order to discover rules or laws, scientific laws, or let's say relationships between various independent and dependent variables. So students create a mental model. We talked about mental models already when we discussed the multimedia learning theory of Richard Meyer. So gradually the facts or the evidence which has been collected in the learning environment by doing research is, let's say, and the conclusions which can be drawn from this evidence are represented in a mental model in a sort of coherent structure in which the various pieces of information come together. In order to be able to research something, there has to be a problem, of course. There has to be a problem in the first place. And this problem is here indicated by various concepts. Anomalous data, for instance, data which do not fit into your idea of the world. My favorite example is the example of a couple of boys in the first grade of secondary education who were confronted with a situation which they did not understand. So the teacher used, these iron sort of, sponge-like structures, and he burned the iron. These iron threads, which are in a sort of, knit together, and he burned them on a Bunsen lighter, so to speak. And he asked the students before he did so what would happen, whether the piece he had in his hands would become more heavy or less heavy by the flames, so to speak, by the burning. And the students answered unanimously, well, of course, the iron will let's say become lighter because of the burning. Things go in the air, and these particles are taken away from the original subject matter or some thing, the iron, and therefore it becomes lighter. Now, well, actually the teacher carries out the experiment and then puts again, beforehand and after, the iron on a scale and to weigh, the iron, and then the conclusion is that the iron becomes more heavy after the burning. And the students can't believe it, so they are completely, flabbergasted. And they first of all they say, okay, we have made an erroneous measurement, so we have to do it once again. And they do it once again, and then they again find this conclusion, and then there should be an explanation. And that's where inquiry-based learning starts. So there has to be something like an anomaly or a cognitive conflict between what you expect to see and what you actually observe. And you have to solve the problem of meeting these two different, sorts of information, what you see and what you think should happen. And then again, of course, there is something like a cognitive change which is necessary in order to be able to understand and to make ends meet, so to speak, to understand what has happened. So that's inquiry-based learning. Now, Ton de Jong with his colleagues made a sort of, picture, I can show it to you, which shows the various phases in an inquiry-based learning project. So first there is something like an orientation on the problem, then there is the conceptualization phase, in which questions are asked and hypotheses are generated, and that leads to exploration or experimentation in the case of hypotheses. So collecting of data, the investigation as it is called, and the data have to be interpreted. And then there's a conclusion. And of course you can imagine that the conclusion leads to new questions and new hypotheses, and these have to be explored again and tested again, etc., etc. And this may be a cyclic movement. I now see I had to review the paper for the Educational Research Review, in which this particular diagram was presented, and I emphasized the cyclic nature of this process, and I now realize that the upgoing arrows are actually representing this cyclic nature of the process of hypothesis generation, testing, and data collection, interpretation, and drawing of conclusions. It's like, what we call the empirical cycle, which has been put forward and introduced by A.D. de Groot, the Dutch great cognitive psychologist and methodologist. Okay, so this is the model, for inquiry-based learning. People communicate, of course, and reflect, and there is discussion, etc. In this column to the right, you can see these labels. And now you can imagine that there is a sort of, a model in the computer program which has to be explored, and which can be explored by actually carrying out experiments. So the program provides the simulation environment in which the research, the inquiry has to be done. That's the basic idea of inquiry-based learning, that the computer controls the simulation environment. Okay, enough of this example. So this is basically an example. You might say that the amount of pedagogy included in the program may differ from one program to the other. So the availability of the model is, and the availability to manipulate variables by choosing values or by measuring outcome variables is important. So the model you should be able to explore the model to a very deep extent, but there's not necessarily much pedagogy in the program that might be included in the accompanying materials, the assignments, the discussions with the teacher and the fellow students, etc., etc. So the blended arrangement of the learning environment. Okay. But of course, you can imagine that there are other programs which actually do monitor and control the way students enter hypotheses or formulate questions by providing sort of scratch pads, electronic scratch pads on which students can actually formulate their hypotheses, and then the program can also monitor that and give feedback on the quality of the hypotheses and the way the experiments are actually arranged to test hypotheses. That makes the program, of course, more complex. Okay, I have 2 examples here. Let's see what happens when I click these. May happen here. I think so, yes. So we are here in the Center of Inquiry-Based Learning. Science kits for children from kindergarten to the 8th grade. Let's try to find an example, perhaps. I don't know what happens. Oh, you see here examples. The solar system, the Earth's crust, energy and waves, cycling of matter and population dynamics. Let's see what happens when we click on the solar system. Oh, and then you just receive a short description. Developed by the center, this kit provides inquiry-based activities designed to supplement textbooks adopted by school districts in North Carolina. Topics include moon log, the sun's path across the sky, day and night, phases of the moon, eclipses, rockets, and solar system weather projects. So what you see here is that that the program actually provides materials, simulation environments for students to do inquiry-based research, but that this is really a blended learning situation in which the textbooks are also necessary and the teacher, of course. Let's see what thrill rides mean. A series of challenges to produce an amusement park ride. Students grapple with inertia, force, potential and kinetic energy transformations, friction, weight, velocity, acceleration, Newton's first and second laws, centripetal force, g-force, simple harmonic motion, net force, and free fall. Interesting. So again, I guess simulation environments to enrich the blended learning situation, learning environment. Okay, so you can see all kinds of examples here. Now let's go back to our presentation, and there was another example. That's the project at Berkeley University. I hope we are yes, we can see that. So web-based inquiry science environment. You see WISE has created a learning environment, virtual learning environment, a powerful online platform for designing, developing and implementing science inquiry activities. Since 1997, growing community, more than 15,000 science teachers, but as well as over 100,000 K-12 students around the world. A simple interface, cognitive hints, embedded reflection notes and assessments and online discussions, as well as software tools for activities such as drawing, concept mapping, diagramming, and graphing. WISE can also incorporate interactive simulations and models built in a variety of modern web technologies. WISE projects promote student self-monitoring through collaborative reflection activities and teacher feedback. As you can see here, perhaps I can enlarge this a little bit. Yeah, so here we are. So you have here an inquiry map which guides the learner with questions, with problems to work on. We have hints and help here. We have evidence pages, provide interactive visualizations and experiments. So the rich science content, that's actually the window where the experiments can be done. And here we have the possibility to ask for predictions, reflection, critiques, to make notes. You see, so this is the typical arrangement of these inquiry-based learning environments, where you have various windows which offer you information in the sense that problems are offered, that hints are given, that you can make notes on a scratch pad, and that you can do the experiments yourself. So you can, the reading and writing prompts, you can predict, observe, explain, reflect. That's of course the usual line of reasoning. You can you evaluate claims, you can write coherent narratives, and you can evaluate as a student the quality of different scientific explanations. Well, I think this gives an example. Perhaps you can explore the website yourself a little bit deeper to see what possibilities there are in this particular virtual learning environment offered by the University of Berkeley. Okay, let's go back to our presentation. And I think as we do this, yes, we come to the third, point of interest here. That's the inquiry-based learning debate. I just provide you with two positions. One put forward by Paul Kirchner, John Sweller, and Clark. The traditional point of view, you might say, and then the other position is by Diana Kuhn. Well, the point Kirchner and colleagues want to make is that guided instruction is more effective and more efficient than inquiry-based learning. It's a matter of human cognitive architecture. We have to do here with, the limited capacity of working memory, the cognitive overload for which Dick Meyer already warned, and the question is that students have to more or less survive, in a learning environment which is so rich and so complex. They cannot even start to remember or learn something. They just have to make arrangements in order to be able to carry out, the assignments. And that occupies all their cognitive capacity, and even more than they have available. So there is an overload of information and demands on the student, and therefore the student is not able to learn something. We have to sequence, we have to guide, we have to provide, step-by-step introductions, a little bit like Richard Meyer also suggested, you might say, in a different sense, because he was focusing on the combination of text and images, the dual channels. So, but that's the position here. So be careful, sequence, arrange everything in order to provide structure. That's the basic idea, what I also emphasize. So structure is absolutely necessary in order to enable students to learn something. That's the basic idea. What is the answer by Diana Kuhn? What she says is she does not disagree with Paul Kirchner, as a matter of fact, but she questions the question which was put forward by Paul Kirchner. So what she says is they do not address what really matters, and that is, what do we want children to learn? Are we considering science as a way of knowing the world, which Karl Boerhaave also mentioned and identified as the design mode of knowledge. We will return to that later on. So the basic idea is whether you want children to understand that knowledge has to be constructed, has to be designed, and that in order to be able to do so, you have to experiment yourself. You have to practice in a more or less, structured and protected and controlled situation, which is the inquiry-based learning environment. You have to develop skills which enable you to do such a research and to build knowledge, to construct knowledge, basically. So Kuhn is actually, let's say, questioning the educational objectives which Paul Kirchner and his colleagues take for granted, I must say. So they simply do not bother about these objectives, and they say, okay, in order to whatever kind of knowledge you want students to acquire, you need to provide them with a structured environment and with a better paced and sequenced and the kind of questions which and appropriate feedback, etc., etc. So the debate is a bit a difficult debate because the points of departure are questioned, not so much the content of what the statements which are made. So what Kuhn is emphasizing, Diana Kuhn is emphasizing, that in order to help children to master, to survive, let's say, the 21st century, you have to equip them with skills which allow them or enable them to construct knowledge themselves. And therefore you need to offer these well-managed and well-structured, but rich and authentic inquiry-based learning environments. That's the basic story here. An interesting debate, I think, still going on. You see the references. You may, let's say, explore this debate further, and maybe it's relevant for your own research. Okay. Now, the next step is a short exploration of what intelligence tutoring systems are. First, some of the characteristics of these systems, then the components, then some examples, which I hope are working, and then some ideas about the outcomes of working with these kinds of systems. Okay, first, the characteristics. Well, the important distinction here is the distinction between computer-assisted instruction and intelligent tutoring systems. CAI, that was the kind of work we were working on when I started to become a student assistant in the 70s of last century. And what we made was, what we designed was computer-assisted instruction. So a focus on end-of-problem support, or support during and at the end of problem solving. That's the main difference. So the end of problem support is basically what we were identifying as, a lot of tests in this more or less, behaviorist approach. So a lot of testing, and the testing is supposed to be a sort of end situation or an end situation, an in between end perhaps in a long road towards mastery of complex skills, but still the tests are used to identify shortcomings or gaps in the knowledge of and mastery of the skills of the students. So, and these tests are used to provide further support and feedback, to provide feedback. So that's why these computer-assisted instruction programs are here identified as end-of-problem support systems. What intelligent tutoring systems do is also provide support during the process of learning or problem solving. So they are providing support during and at the end of problem solving. That's one of the differences. So whenever a program provides support when the student is trying to solve a problem by commenting on this solution process or by providing hints or whatever, then we talk about an intelligent tutoring system. And of course, this tutoring cannot be provided unless the system disposes of a model of the subject matter and a model of the student. So basically, these ITS systems do provide tutoring, provide guidance by comparing, actually. Well, we are going to see that there are several systems, but one of the ways they operate is by comparing the subject matter, so the ideal knowledge, with the current knowledge of the student, which is supposed to be sort of, incomplete replica of what has to be acquired, what has to be learned, what has to be mastered. So the student is coached because of his or her incomplete mastery of particular problem-solving skills or complex, reasoning skills or whatever we are talking about. So that is what intelligent tutoring systems do, and therefore they are more complex and more ambitious, definitely more ambitious than, let's say, simple computer-assisted instruction programs. Okay? Now, some components. I was already discussing that. We have a model of the domain knowledge. So there is something like a representation of the knowledge as it has to be acquired by the student, in terms of statements, in terms of, if then else constructions, in terms of production systems or whatever kind of logical, representation system you're using. Lots of these programs are written in C or C++, or other languages which are really have been developed for the purpose of representing knowledge. And of course, we can talk about more complex systems, like the system ACT-R developed by John Anderson, for instance, which is based on a complete theory about the acquisition of cognitive skills. So these systems can really be very complex, and of course you can imagine that the representation of the knowledge to be mastered has to be flexible and has to be addressable in order to be able to use that knowledge to provide guidance to students working in the system. And then there is also the dynamic student model. Of course, that's the model which represents the extent to which students actually master the knowledge or skills to be mastered in the end. And this student model may be a sort of derivation of what the expert knowledge is about, or you can imagine that there is another structure which is necessary in order to be able to represent the student model. This model is constantly updated, well, you can imagine that you actually evaluate the student's performance by analyzing what kind of knowledge a student uses in order to be able to solve a particular problem. For my PhD work, I actually developed a system, a very simple system, which you might call an intelligent tutoring system, because I had a set of, I don't know exactly, let's say 20 rules which governed the solving of particular problems having to do with selecting, job applicants for a particular job in a simulation environment, of course. So what the students did was learn how to select the job applicants, to ask questions about, the applicant's background, interests, etc., etc. And well, you could match these characteristics of the potential candidate for a particular job with the job description, and the way you did so was governed by particular rules, and these rules were, of course, the skills or the strategies applied by the job counselor, for instance, and the student was the job counselor. Okay, so what I did was I actually analyzed and parsed each action of the student and matched it with the rules to be mastered. And whenever there was a rule violated, I started to explain what you now did was not very wise, because you should keep into account that, and then there was sort of explanation of the rule. But when the student actually did comply with a particular rule, then I said something in the program like, this is very well done, because you have actually carried out this very diligently or elegantly or whatever. And I remember that the students, of course, did not, my participants were not, did not possess these rules. They were just, working on the problem. And they were sometimes very astonished when the program all of a sudden complimented them for actually applying a rule they never had heard of, but they were apparently using in a particular step in the problem-solving process. So anyway, so that's what these intelligent tutoring systems do. They compare the active student, parse it, and interpret it in terms of the rules, which are represented in the domain knowledge model. Then there is something like a pedagogical model. Which says something that you shouldn't, be too strict on warning students for violating particular rules. You should be a bit, lenient, or just organize your feedback in a positive way, or providing examples, or relating what the student actually did with what he previously did, etc., etc. So all kinds of pedagogical arguments which help you to arrange your feedback. And then there is, of course, the user interface, which enables the student to work in the learning environment. with all tools which are necessary to carry out, to solve problems and to carry out assignments, etc., etc. So these are the four components of an intelligent tutoring system, and you can imagine that the first two are the most important, because they do the work, and the interaction between these two models actually determines the advice the student gets, or the problems which are offered, etc. Okay, so these are the components. Perhaps an example. I have two examples here. The cognitive tutor. The cognitive tutor is actually a sort of, concrete elaboration of Anderson's XR model. So it's from Carnegie, of course. And perhaps I can show you a little bit of this intelligent tutoring system. The cognitive tutor. Well, you can also explore this website yourself. The focus is on the individual student's needs with software that customizes feedback, hints, and prompts within each problem. With cognitive tutor software, students in grade 9 to 12 have all the resources they need to succeed. So there are lessons, key terms, skills students should, let's say, explore before they start working on problems. There is a glossary, there are step-by-step interactive examples, and then there is something happening here, and I not exactly know what happens, but should I press this big arrow? It's always enticing, of course, to do that. Let's see what happens. Well, we have to do something which is not possible at the moment, so I just return to my presentation. And then there is a second example, which is Sherlock. And the interesting thing about Sherlock is that it has a different architecture. Therefore, I would like to mention it, is this one. It is a system in which students have to diagnose electronic circuits. It's very difficult. I try to give you an example taken from this particular presentation, but I couldn't make it clearer than it is now. The point is that so the student experiments by probing particular connections in this electronic system and seeing what happens there, and with all the particular elements which you can find in resistance and resistors and whatever you have there in such a system. But the interesting thing is here that there is not a comparison between the knowledge to be mastered and the knowledge as shown by the student, but there is always, in every situation, the system compares the problem which is at that particular moment on, let's say, the board, with the solutions which the system has already stored for all kinds of problems. So this is what the authors call case-based reasoning. So case-based reasoning is different from the reasoning which has been implemented in systems in which a comparison is made between an expert model and a student model. In case-based reasoning, the particular problem is always, solved by taking refuge to already existing solutions in a large database. It's a bit like, chess players, how chess players think. Chess players have an enormous amount of solutions, of board positions and solutions in their head. For instance, something like 50,000, which is often mentioned as a sort of, number of solutions experts have in a particular domain, 50,000. Well, what a chess player does is, in a particular situation, try to identify this situation in, this large database of problem situations which he has stored, which he or she has stored in mind, and extracting the connected solution procedure for that particular problem. So case-based reasoning is identifying cases and identifying the attached solution to a particular case. Okay, that's done in this particular Sherlock in this particular intelligent tutoring system, and the student gets feedback based on this, case-based reasoning by the system. Okay. Now, perhaps a few words on the effects of intelligent tutoring systems. I found in the review of educational research a meta-analytic review in which 50 controlled evaluations of ITSs, intelligent tutoring systems, were actually taken into consideration. And well, of course, these are from various circumstances with various kinds of students, etc., etc. So it's perhaps difficult to take them together as one group of tests of ITSs. But in general, there was always, in these experimental situations, a comparison between the ITS and the conventional learning environment, and there was always a plus of 0.66 standard deviations for the ITSs in comparison with the conventional tutors from the 50th to the 75th percentile. Of course, it depended a lot on the post-test used and the control treatments used, whether you did find or did not find such a difference. But it is considerable, I think. But it did surprise me, as a matter of fact, because you can imagine that it is an enormous investment to create these intelligent tutoring systems. Then they have not found their way, I think, to the classroom, as might have been dreamed by the original people who started to work on these systems, like Alan Newell and, of course, John Anderson himself and other people. They were thought of, these ITSs, in the 90s or the 80s and the 90s of the last century as a solution of many educational problems, but they have not been in that way successful. But if you see the gradual development of these systems and the still increasing power of these systems, then I must admit that the effects, as shown here in this review study, are considerable and are hopeful for the future. Okay. Now a few words on serious gaming. Serious gaming is, of course, something which we all are, to a certain extent, a bit familiar with, as far as we are familiar with gaming. But gaming and games and serious games are, of course, not the same. So games are for fun and serious games are for serious business, of course. You can imagine educational applications. So Meyer again gave a few characteristics of these serious games. And these characteristics are also perhaps the reasons why people like to play with these serious games. So first of all, they are rule-based. So there's an environment which you can explore and which you can try to understand. So that is already, of course, a lot of challenge here, curiosity, which is raised by these games. Then games are responsive, the actions are followed up, which is also, of course, very important. You see what you see the effect of what you're doing in the game environment. They are challenging. The goals are of ever increasing difficulty, of course, as you know the various levels, etc. And they are cumulative. That is, past successes are recorded and are used for reflection by teachers or whatever people that are in your environment who want to help you to become better in a particular game. So these characteristics do, let's say, invoke the curiosity of the students and the fantasy of the students, and also the challenge, the need to be challenged. And these characteristics are very old, acknowledged characteristics of students, which make them very eager to play games. Okay, so these characteristics are also perhaps a point of departure for doing research on the effectiveness of serious games. The gamer disposition here is identified by Brown and Thomas, Gamers like to be evaluated, not for reward, but for improvement, because of course there's a constant evaluation. Gamers play in diverse teams. Gamers thrive on change. They want the environment to change and to be challenging and new in various respects, etc. Gamers see learning as fun, and gamers explore radical alternatives. So these characteristics of games are of course interesting and important when you want to create game-based learning, and when you want to use these serious games as an opportunity for students to learn. An interesting thing here is that people have tried to find out whether games are helpful in attaining the so-called 21st century skills. And you can see that complex collaboration games do in fact contribute a lot to attaining these strategies like planning and like reflection and like evaluation, etc. Strategy games also do, tactical games do, collaboration games again, and gradually games with competition and games with, let's say, choice and fidelity and fantasy are less contributing to these 21st century skills. So interesting that these collaboration and strategy characteristics of games are really important to make them feasible for acquiring these, complex skills. Okay. Again, let's try to figure out whether games actually whether students do actually benefit from games. So let's see, Meyer, who wrote this particular paper, actually identified various genres of game research and also said something about the cognitive and the motivational effects. First of all, the genres. Three kinds of genres of games, game research. First, which features of the game promote learning? That's the added value kind of question. And what you do is, you have a base version of a game and you have an enhanced version of a game, and just compare the two to see whether these enhancements actually do the work and play the trick you want to play. So whether these enhancements actually promote learning. So what does the game add, in fact, to the learning environment? And then the second question might be, what do people learn from game playing? So what is the effect? What do they learn? What's the cognitive effect? And so you can test that in a situation where they have to answer questions or whatever, write something or give an analysis of a problem, etc. And then you just compare students who played the game with students who did not play the game to find an answer to that particular question, the cognitive consequences. And then there is also the media comparison. So you can imagine that you use a game, but you can also show a video or use a book or a text. And you can, so in this way, compare various media in order to figure out whether the game as medium does the trick. And so you just simply compare the game with standard media in which the same information is transmitted. Again, this is based on the idea that something has to be learned from the game, and you can measure that, which is basically, let's say, the transmission idea, which makes the comparison possible. If you say, for instance, that students have to create new knowledge, and that a game enables them to do so by exploring all kinds of environments, etc., then it is far more difficult to make a comparison within a conventional situation in which this information simply is not available. So Meyer is always, a very clear writer and a very clear thinker, but I must admit that in the end, at the end of the day, as it is called, he is working usually from the cognitivist perspective, whereas the whole idea of constructing knowledge, which we will encounter later on in this module, is not very much his cup of tea, so to speak. Okay, So these kinds of research have been done, and are and the question is then, what do we find? Again, there are some differences, although not that, let's say, impressive as we saw with the intelligent tutoring systems. So there are some gains. As you can see, the deltas are there, and they are significant. As far as cognitive effects are concerned, this is a review study done by various people, including Herder van Oostendorp, who used to be a close colleague when I worked, and he worked in Amsterdam. Meta-analysis of cognitive and motivational effects of serious games. You can find it in the Journal of Educational Psychology. And you see that there are cognitive effects have been identified with significant outcomes. Higher learning gains and also higher level of retention compared with conventional media. And motivational effects could not be identified. Interestingly, I must say, because my idea was that the motivation effect, the challenging, the curiosity, the fantasy kind of things, that's what make people, love games and work in games. But the effects are not that substantial, as we can see here. Okay. Then we pay attention to massive, open, online courses. That's a new development, must say, in multimedia learning, but it is a rapidly developing area. In January 2016, according to the sources I have read here, I have included the references here. There were in 2016 all over the world something like 4,500 courses and 35 million students, and 12 MOOC providers all over the world. So again, I can try to show you, although I become a bit hesitant now, some examples. We're now looking at Coursera. Coursera is a very big, database with courses which have been developed all over the world. As you see here, we have I just picked out a course, Ancient Philosophy, Aristotle and his Successors. This course has been created by the University of Pennsylvania. The course is taught by Susan Sauvé-Meyer. She's a professor at the Department of Philosophy. It's 5 weeks of study, 1 to 3 hours per week. The language is English. You have to pass all graded assignments to complete the course. And the average rating is 4.8, which is not bad, I must say. Now you get the syllabus here. So let's have a look at it. So in week 1, you have 6 videos, 1 reading, and then you have to do some work, and then again 6 videos and 2 readings. In the week 2 about Aristotle's natural philosophy, etc., etc., etc. So it's very detailed, this description with all kinds of assignments to show that you have understood what has been explained. In general, I must say that what I've seen, I've actually explored a couple of examples before I started to work on this particular course myself, that what you see is that people are just standing, before the camera, as I am doing now at the moment, and just, with a blackboard behind them or a whiteboard behind them and just teaching like they do in a classroom. So there's not much modern technology involved in the way they transmit their expertise. That's interesting. It does, I think, to a considerable extent also hold from my course here. But still, the idea of being independent of place and time to follow the course is of course a major asset of these courses, but not so much the pedagogical tricks which have been applied. In general, you can follow these courses for no money. for nothing. But as soon as you want to take an exam or want to be evaluated, then you have to pay. So that's the deal in almost all of these courses. So you can study everything if you like, as long as you don't take a test. As soon as you take a test, you have to pay. And then you will be evaluated, of course, and then you're actually enrolled in the course. Okay, that was Coursera, a very large database, as I said. And I have another example here, the edX. So this is also an opportunity to do online courses with contributors from very distinguished institutes like MIT, Harvard, Berkeley, the University of Texas System, and the University of Queensland, and also our own technical university, Delft, TU Delft. And then you have, again, so these are quite technical things I suggest. So I have the feeling, so statistics and R, introduction to Python, interesting things. Now, as soon as I finished, designing this particular course, I might start as an pensionado to work, for instance, on Python, which is an interesting language, I think, to learn. Anyway, and also more literary subjects here, like justice, etc., English composition. You see? So that is edX, also an interesting area to explore, perhaps. And I had another one. Oh, that's the Delft thing. So you can see the TU Delft has been very, very advanced in also developing these courses like pre-university calculus, business model implementation, etc., etc. Let's have a look at this one. Pre-university courses. Well, you get an overview. The course consists of 6 modules and 1 final exam. The class will consist of a collection of 3 to 5 minute lecture videos, inspirational videos, and the use of mathematics in science, engineering, and technology, interactive exercises, homework, and exams. So you shouldn't expect much, let's say, new ideas about the pedagogy, but it's as I said, very helpful to do courses in your own time and at your own place. That's the basic idea of MOOCs. Please have a look yourself to be able to further, let's say, get an impression. Completion rates are extremely low, 10 to 30%, which is a big problem. A problem of these courses, but also a major problem of Open University courses, where the same problem existed for a long time. You can identify various types of users. So people who just register and do not further let's say, contribute to the course. You have the active learners, of course. You have the gamblers who just take a test, see what happens, and the social learners who do make use of the let's say, social environment of the MOOC by communicating with fellow students, etc. So there has been analysis of dropout rates, and there has been a relationship between reading and writing and discussion forums. So you can imagine that people who are more active in these fora also drop out less. That is a simple thing. So the active instructor drives a positive interaction into creating a dynamic social environment. Activities are always important as far as keeping people in these courses is concerned. 3 ways to improve retention. Student pacing, we already discussed that in Meyer's theory. Rewards for completion. More rewards for completion, so make it a real issue that you are rewarded if you do a test and take a test and have success. And more interaction between students and between students and teachers. These 3 let's say, measures actually have been proven to lower the dropout rates of these MOOCs. Okay. I think that ends our discussion and first exploration of technology-enhanced learning environments. I hope you have let's say, now got the opportunity to have a first idea of what these environments are about, what their ambitions are, what their purposes are, and what the possibilities and also drawbacks of these environments are. And I hope you also were able to connect what we have seen and discussed with the multimedia learning theory of Richard Meyer.